Okay, so we're considering then thin cylinder theory, and examples of thin cylinder theory, pressure vessels, are shown here. And they're all around us, these thin cylinders. When you start considering the topic, you suddenly realise that actually there's a lot of thin cylinders and lots of applications you've never really thought of. And your cola bottle is one straight away. Your cola bottle is actually designed as a thin cylinder using the theory that we're going to consider in this presentation, as is a cola can. That's designed as a thin cylinder. So plastic bottles and aluminium or steel cans, they're designed using the theory we're going to review here. So the boilers of a steam train also designed to be a thin cylinder, and the theory we're using can be applied to them. A road tanker, the tanker here, the cylindrical part of the tanker there, that's designed to be a thin cylinder. And of course, things like zeppelins, it's a bit beyond where we're going, but they'll be designed, their fabric will be designed as sort of thin cylinder theory. Sort of close to my heart, I guess you could say. Fuselage skin panels, they're designed based around the theory we're using today. Certainly where you've got no discontinuities in the structure, so sort of the skin up here, for example, the top of the cabin, in the fuselage, that would be designed basically using some of the theory that we're considering today. And any pipe work, considering pipe work in chemical plants under pressure inside the pipe, again, you could apply the theory we're considering today to that kind of application. This is a photo of a gas storage container, and you notice here it's actually a spherical container here. So not only do we have cylinders, like on the right hand side, that's a cylinder that's under pressure, we also have spherical vessels that are under pressure, and again the theory we're going to look at today will design the spherical vessels as well. So as I said, these kind of things are all around us, these sort of applications of thin cylinder theory is all around us really, and we just probably not aware of it. I'm just going to do some very brief recap here, just 2 slides of recap, because these little topic areas will crop up in some of the questions we're looking at. And the first one, just to mention a factor of safety. We've covered this many years ago, probably now, FOS as it's sometimes called. The factor of safety is defined as the maximum allowable stress, and that could be the ultimate tensile strength, the UTS strength, which would be that value there, sort of failure stress up there. It could be the yield strength, could be the maximum allowable stress, the sigma y, which would be sort of this point here on the curve, or it actually can be any other value that's specified, because something we haven't considered and we're actually not going to consider is buckling or stability of members, and sometimes that can affect the allowable stresses. So there are other stresses that can be used, but so ultimate tensile strength or the yield strength. But that'll be given in the question if we need that. So factor of safety is maximum allowable stress divided by what's termed the permissible or the working stress, and that's the stress the component's allowed to work at every day of its life. So that would, for our sort of topic area here, that would mean the pressure vessel is working to this stress, or it can work to this stress every day that is used. Okay, so you might see that formula used in some of the questions, only a few, but it might mention factor of safety. Another thing I'll just mention is conversions. We considered a few weeks ago now unity brackets and conversions from various quantities, and you'll find in this work we will be flipping between different units, perhaps I should say for different quantities. So pressures in meganewtons per meter squared, or they might be in megapascals, which is the same thing, or they might be in newtons per millimeter squared, or you might get pressures in terms of a bar. So the questions kind of come at you at different directions with different units. With static analysis, I said to you before, I'm not really bothered whether we use millimeters or meters here. As long as we're consistent in our calculations, then it's fine to use millimeters. If we were studying dynamics, then I always emphasize we should use meters. But in this kind of work, we can use millimeters if we want to. We just need to be careful with conversions, information given in the question. So I've just highlighted on this slide the use of unity brackets. You may not want to use them because you may know the conversions, but if you did want to convert, for example, 20 bar and you want to put that into megapascals, so the conversion is from bar to megapascals here, then using our unity bracket, the conversion would be a 1 megapascal divided by 10 bar, because there are 10 bar in 1 megapascal shown above. So our conversions, don't forget, are always of cancelling unity brackets. So in this case, the bar on the top, the 20 bar, has to cancel with the bar on the bottom to produce the final answer in terms of megapascals in this particular case. All right, so 20 bar is equivalent to 2 megapascals. So that's using the unity bracket. You'll get very familiar with the conversions anyway, so I doubt you actually use any unity brackets, but this is how the conversions work. And if you want to say to convert a pressure from newtons per millimeter squared into bar, for example, then 4 newtons per millimeter squared, the unity bracket in this case would be the bar upon the newtons per millimeter squared, because again they're cancelling unity brackets, so you have to cancel the millimeter squared with the millimeter squared, so 4 newtons per millimeter squared is 40 bar. Another conversion that will crop up, I'm sure we'll come across this in some of the questions, will be the conversion from a stress in newtons per meter squared into newtons per millimeter squared. Be careful with that. If you have say 165 meganewtons per meter squared, 165 million newtons per meter squared, then the conversion to put it into millimeters squared would be the 1 newton per millimeter squared over 1 meganewton per meter squared. Actually the same value. And again, we've got this cancelling effect of we're cancelling the meganewtons per meter squared to leave us with newtons per millimeter squared. Okay, but again, you'll probably get very familiar with 165 megapascals or 165 meganewtons per meter squared is 165 newtons per millimeter squared. So you'll get familiar with the conversions, but if you did want to use unity brackets to help you structure a conversion if you're unsure, well, that's the process involved. And we have a lecture on that if you want to review that. So we're analysing what's called thin cylinders. So the classical approach is to consider a cylinder that's remote from the ends or any discontinuities. So this theory is very valid in a thin cylinder, but it's valid when you have what's called discontinuities, no cutouts in the structure, or you're not near a flange, for example, because if you're near cutouts in flanges, you get change in stress patterns, and that causes stress concentrations. And this theory doesn't account for stress concentrations. You need slightly more rigorous analysis to account for stress concentrations. But anyway, you've got a long length of pipe that's uninterrupted, a long length of tube, a cylinder, then this theory is very valid. It gives very good results. The only consideration we have to be careful of is that the diameter to thickness ratio, called the D/T ratio, has to be greater than 20. Okay, and for all the work we're going to look at, they will be greater than 20. Some are very much greater than 20, but they certainly have to be greater than 20 for this theory to be applicable to what we're going to do. And if you have a cylinder of those characteristics, then we can quite realistically assume that there's no variation in what's called the hoop stress across the thickness of the vessel wall. And it acts like a membrane. It acts like a balloon, effectively. So what that little slide is trying to say, that across this cross-sectional area here, sort of across that section there, the thickness, the stress is the same all across that section. So inside to outside diameter, we assume that the stress induced is the same. And the two types of stresses you'll see we'll be considering will be the hoop stress, which is also called a circumferential stress, and also a longitudinal stress, sometimes called an axial stress as well. Those are the two types of stresses that we're going to consider. We'll go into those in a bit more depth in a moment about what they are. And also, we have an internal pressure P applied in all our vessels. The dimensions we're considering, we've got the diameter D and the wall thickness T. Okay, so we'll look in this much more detail, but that's sort of generic overview of it. So as long as we've got a section that's well away from the discontinuity, the ratio of D/T is greater than 20, and then we can assume the thin cylinder theory applies. And the reason why we want to use thin cylinder theory as opposed to what we'll look at in a few weeks of thick cylinder theory is it's just much easier to apply. It's just very simple. You'll see the formulae we're going to derive in are very simple to use. So engineers like it because it gives very accurate results very quickly for a section that's classified as a thin cylinder. So that's why we like to use this theory. This just recaps, this just overviews the two types of failure we've got in our thin cylinders. There's what's called the hoop failure, something called a circumferential failure, and the hoop stress shown there. It's sort of like tearing blowing the two top and bottom parts of the cylinder apart. So that's called a hoop stress. We'll define that in a moment in our derivations. There's a longitudinal stress, which is a failure, as you can see here. So actually here we're failing, sort of being pulled apart in the axial sense. That's called longitudinal stress. So those are stresses for cylinders, circumferential and longitudinal. And we'll also look at spheres or hemispheres, and that's like the football looking, like the gas tank I showed you previously. And in that there is only what's called a hoop stress, just a hoop stress in that particular vessel. We'll look at that again in a moment. So those are the types of failures for our cylinders and our spherical vessels that we'll be considering. Here's a fuselage, an aircraft fuselage, aircraft section here. It's showing the fuselage, and where we have no discontinuities, then the thin cylinder theory kind of applies reasonably well. So sort of in that panel there, for example, if I wanted to work out the stress due to internal pressure alone, then I could get an estimate of it from using the formulas that we're going to derive in the thin cylinder presentation. This is an example I found, just a photograph. It shows the ALOA, what's called convertible failure, and you can see quite clearly here that the top of the fuselage is completely disappeared in flight. It became what's called convertible in flight, but it managed to land on the ground okay. But clearly we can see we've got kind of a failure like this. We've got a circumferential failure. The top of the fuselage is completely blown off, because it should be here, but it's completely blown off in flight, and that's a circumferential failure. I'm not sure what the actual cause of that was. But you can see these kind of failures do occur. And just to show you that all sorts of disciplines have thin cylinders, this is actually a pressure vessel associated with a nuclear power station. Okay, so I can't really see it very well, but there's the sort of vessel here, and it's a sort of vessel wall I'm showing there. And the vessel wall is 2 inches thick, 50 millimeters thick. It doesn't actually say what the diameter of the vessel is, but I would certainly think that would classify as a thin cylinder that's subjected to internal pressure there of 100 psi, it says. So all sorts of disciplines, thin cylinders can crop up, not just aircraft and trains and fizzy Coke bottles, but in your nuclear power stations also you can have this sort of thin cylinder consideration to design. Okay, so we know cylindrical or spherical pressure vessels is the topic area here, thin cylinders, and we've already mentioned it, plastic bottles, fizzy drink containers, gas cylinders shown here, and aircraft fuselages, cabin structures. They're all analysed as, or they can be analysed as, thin cylinders. Let's go through some of your notes. You're going to browse these with you. This is some thin wall cylinders, background and assumptions that we're considering here. So thin wall cylinders, they're used for pressure storage. Practical examples already mentioned in the food processing industry of tanks, chemical storage tanks, aircraft fuselages, balloons, fizzy drink containers. A thin cylinder theory assumes that the component fails in one of two ways. It can fail circumferentially or it can fail axially. The stresses associated with these two failure modes are termed the hoop stress, and I use the lowercase sigma here for my stresses, so sigma h would be the hoop stress, and longitudinal stress, sigma L. They're shown in the figure here. So sigma h is going in, it's showing direction in the circumferential direction, and sigma L is in the longitudinal direction. Just to put a bit of a jargon word for you, but these hoop and longitudinal stresses are actually determined principal stresses. In other words, there's no shear stress on a principal stress. So it's just a pure direct stress, a pure tensile stress is shown there in the hoop and in the longitudinal directions. There is actually a third stress on the vessel, termed the radial stress. I'm just trying to show it here in this diagram. It's not in your notes, this. But I just showed you there that radial stress. Now, that would make it what's called a triaxial stress situation, and it would complicate our analysis. Now, what we find with thin cylinders, and I'll show you this in the examples we're going to look at, is that the radial stress, and the radial stress is actually equal and opposite to the pressure. So whatever your pressure in your cylinder is, if the pressure is 10 megapascals, then your radial stress would be negative 10 megapascals. It's always equal and opposite to the pressure. But what we'll find is with thin cylinder theory, the radial stress is essentially zero. All right, so for a thin cylinder, the radial stress is effectively zero compared to the hoop stress and the longitudinal stresses. They're much, much larger. So again, it's assumption made in thin cylinder theory, but that radial stress is ignored because it's negligible. It is there, but it's just small compared to the other ones, so we can ignore it, and it doesn't really affect the overall analysis. And again, just another minor point, in some textbooks, the hoop stress is denoted as sigma 1 and the longitudinal stress is denoted as sigma 2. That's a sort of a nomenclature issue. For principal stresses, they sometimes denote them as sigma 1 and sigma 2, but our sigma 1 is our hoop stress and sigma 2 would be our longitudinal stress. Sigma 3 would be the radial stress, but that's 0 in this case. So just be aware of that notation. Okay, so effectively we've just got two stresses. We've got biaxial stress situation. In other words, we're ignoring the radial stress, but it is there. It's just very small. Continue with our background assumptions here. So based on the assumptions we've considered so far, we can actually use what's called static equilibrium to solve thin cylinder problems, and that makes them easy to solve. But of course, we've made some assumptions to make it that straightforward. We also need to be aware that in all the work we're considering, the internal pressure P shown here, must be greater than the external pressure. If the external pressure is greater than the internal pressure, we could have buckling effects, and that's really complicated. And in pressure vessels, we're always assuming that the internal pressure is greater than the external pressure, so there's no chance of it buckling. So that's something we'll assume in all the work we're going to consider. And also we need to consider the d upon t ratio. As I said before, the cylinder diameter, little d shown there, must be at least 20 times the thickness of the vessel. So d must be greater than or equal to 20t. Otherwise the cylinder theory starts to fall over a little bit. So we need to be careful of that. So diameter here shown in d must be 20 times the thickness at least for this cylinder theory to apply. And just again, another minor point with notation. Different textbooks again use different notation. I'm showing lowercase d here for my diameter, but in some textbooks they will use capital D. Okay, and in fact I will use capital D in a lot of the work I'm going to do. So my lowercase and uppercase d's are interchangeable, and that also is the same with pressure. Some textbooks use pressure as capital P, some use it as lowercase p. You'll see I use both in the work I'm going to consider. All right, so just don't worry too much about the notation there. A little d is the same as a big D in the work I'm going to consider here. Continue on with our assumptions. The mass of the container and its contents, they're also considered negligible compared to the internal pressure applied. So whatever the fluid is inside, we're not really bothered about it because we're saying the weight of it, the mass that we've got is not going to cause any issues as far as increasing the pressure. And all pressures that are stated are going to be gauge pressures. That's pressures above atmospheric. Okay, so by default, any pressure we're given is above atmospheric. So this type of structure is sometimes termed a shell, and as a shell, it can only accommodate what's called tension or membrane stresses. So like a balloon, in other words, a balloon, if you think of a balloon, there's only tension in a balloon. It has no bending stiffness. It can't take any bending, no bending stiffness in a membrane. So that's effectively how we're considering our vessels, even though the metallic materials, we're considering them in that vein. Okay. Thin-walled vessels, it's negligible radial through the thickness stress. We're also considering that stresses are assumed to be evenly distributed throughout the wall thickness. Hoop stress at the inside wall is the same as the hoop stress at the outside wall. Because it's so thin, we're assuming the stresses are the same. Let's look at the derivations for circumferential and hoop failure. So let's consider the equilibrium of half of a cylinder. Half of a cylinder shown length L in our picture here. Okay, we've got an internal pressure, P is applied, lowercase here. We've got our diameter, D. Here we've got a wall thickness, T over here, and we've got a stress. They call it sigma 1 here. They actually mean a hoop stress. We've got a stress on the vessel wall. So that sigma 1 there is this sigma stress here, which is actually really the hoop stress we've got in the wall there. Okay. If we look at the pressure applied, imagine it's internal pressure in this particular case. To work out the applied force from the pressure, It would simply be the internal pressure given in the question, so pressure P, multiplied by what's called the projected area, and the projected area would be this kind of area here, which would be D times L, in other words. So there's a proof behind that, but I think we can accept that pressure that's applied all around that circumference, the actual effect as far as a force is concerned, it would be pressure times the D times the L. That would be trying to push that half of the cylinder up the page, if you like. There would be the force, if you like. It's not showing the force there, but there's a force that's being applied there. Call it F, and that's its applied force shown here, okay? Pushing it apart. Now what reacts that, what holds that top of the vessel to the bottom of the vessel is basically the reaction along the lengths of the wall here. So if we multiply the hoop stress, I call it stress 1 here I know, if they multiply the hoop stress by the area of the cylinder wall, so the area of the cylinder wall would simply be the thickness of the wall, so that little thickness there, times the length of the wall, the length of the vessel wall, times 2, because of course we actually have 2 sides, we have a side over here as well. That would be the reacting force. So what that calculation is trying to do there is to work out the reaction force. In other words, it's working out what the force is going to be that's pulling down, if you like, on either side of that vessel. That's kind of the reaction force that we've got to the applied force. The pressure is trying to push that top of the cylinder up the page, and our stress times the area is trying to keep it where it is, kind of keep it in equilibrium. So if we equate the equations 1 and 2, there's 2 equations shown here. If we equate equations 1 and equation 2, we get this expression. PdL, which is this one, is equal to the hoop stress multiplied by twice the thickness and the length. And we can simply rearrange the equation now. If I rearrange it to find the sigma 1, the hoop stress, that will become PD upon 2T. And there's our first derivation. For the hoop stress in the cylinder, the stress in the wall, across the entire wall, is the pressure times the diameter divided by 2T. And the diameter is actually internal diameter in this particular case, but we're not really bothered whether we're considering internal diameter or external diameter or mean diameter even, because the wall thickness is so small, it won't make any difference really to the calculation. It's very minimal difference in stress between inside and outside of the wall. So that PD upon 2T formula, the diameter we use there can be the inside, the mean, or it can be the outside diameter. It really doesn't make a lot of difference to the final stress. Let's consider longitudinal failure, a second failure we need to be aware of here. This is where, as it shows in the sketch there, we've got the 2 halves of the cylinder being forced apart in a longitudinal sense. On this diagram here, they've called it sigma 2. It's the stress in the wall. That's basically a longitudinal stress. So what we've got here effectively now, if you think of the end caps of the vessel, the end of the cylinder here, we've got our pressure applied, so our internal pressure is applied here, and it'll be applied all the way across the end of that vessel, a circular vessel here. So if we wanted to work out the force, it's now pushing the vessel apart in a longitudinal sense. So in other words, I'm trying to work out a force, if you like, in this direction. So the pressure times the area is producing this force here. It's forcing, there's obviously force there as well. Okay, if I want to work out that force that's applied here, then the force F is simply going to be the pressure times the area. So the pressure times the area, and the area is going to be pi d squared divided by 4. Again, d is the internal diameter here. Okay, that's the force that we're trying to push those ends of the cylinder apart there, okay? So that's equation 4 as it's shown there. What's reacting that? Well, what's reacting that is going to be the stress, the longitudinal stress that we'll have in the vessel wall. So the stress is in this wall here, multiplied by the area of that very thin cylinder wall. And we can work out the what they call a reaction force here. We can work out what that is, that reaction force. It's opposing the F, because it will be the longitudinal stress multiplied by pi multiplied by the mean diameter multiplied by the thickness. What you'll find is if you've got a very, very thin wall, so that the T is very thin compared to diameter, you can actually work out the area of the circumference of the wall by simply multiplying pi by the mean diameter times the T. That formula only applies if you have a very thin wall compared to diameter, but it's a very valid formula to use. So I can actually work out what the area of my cross-hatch section there is for the longitudinal area by pi d mean times t. Multiply that by the stress that's in the wall, I'll get the reacting force from the vessel. So again, as we did in the previous section, we're going to equate equations. There's equation 5 there. Equate equations 4 and 5 here. So there's 4 equated to 5 here. And if we rearrange the equation, we can now find the sigma 2 or longitudinal stress. And that's simply PD upon 40. Now, okay, so very similar formula to the hoop stress. It's just that the longitudinal stress is actually half the hoop stress. It's PD divided by 4 times T. That's called the longitudinal stress. The longitudinal stress acts what's termed on the diametrical section. Acts on the there's a whole cylinder there. Just showing you, trying to show you what the areas again were. That area there would be the area calculated around there, and that's based on using the mean diameter of the vessel wall, this pi d squared upon 4 calculation. Now that calculates the area that's sort of inside the vessel itself, okay, when we're working out the force supply. Exercise 1, we've got a compressed air tank, has a diameter of 300 millimeters. We're not bothered with that inside diameter, outside diameter, mean, it doesn't matter. The diameter, as far as we're concerned, of 300 millimeters and a wall thickness of 10 millimeters. We've got to calculate the hoop and the longitudinal stresses induced within the vessel wall here, the shell wall, and we're given an internal pressure applied. The internal pressure is actually 4.15 megapascals. So we've got to be careful here. We've got the dimensions given in millimeters, and we've got the internal pressure given in megapascals, meganewtons per meter squared. I notice that the answer is in terms of meganewtons per meter squared, so just for the sheer fun of it, I'm going to put all my values in millimeters just to show you a contrast between the units here. We're given the diameter, so D is equal to, in this case, 300 millimeters. I'm going to use millimeters. We're given the wall thickness T, and that's given as 10 millimeters. And we're given the internal pressure, P. Now, pressure is given as, in the question, 4.15 megapascals. But if you go back to our unity brackets, I'm not going to use one here to save time. If you go back to unity brackets, you'll find that can be converted to a pressure in newtons per millimeter squared as 4.15 newtons per millimeter squared. These are kind of conversions we need to try and get familiar with if we can. So I'm going to use that value in my calculations. So my stresses will come out in newtons per millimeter squared. Okay, wants us to find the hoop stress and the longitudinal stress and so on. So let's do the hoop stress first of all. So hoop stress, also called circumferential stress. Use my sigma h, and again sometimes lowercase h is used, uppercase h, different symbols used in different textbooks. So PD upon 2T is the formula we're going to use, and that's equal to, in this case, my pressure, 4.15, multiplied by my diameter, it's in millimeters here, it's 300 millimeters, all divided by 2, multiplied by the thickness, and the thickness is 10. I get 62.25, that would be newtons per millimeter squared, but the answer is given in terms of meganewtons per meter squared, and that's the same value. So 62.25 newtons per millimeter squared is the same as 62.25 meganewtons per meter squared. We've got the same things. And then it wants us to find the longitudinal stress. You probably have already done that by the time I do this. So longitudinal stress, that would be sigma L, use my notation. That would be P D upon 4T. So we can see actually that's simply going to be the hoop stress divided by 2. So dividing by 2, we will get the 31.125. And again, I've worked in millimeters squared there, newtons per millimeter squared. So I've rounded up here. It's the same as 31.13 meganewtons per meter squared. Exercise 1, full solution. So a cylindrical pressure vessel with failure in shear. Now, we don't really have all the theory to really understand this level, but anyway, I'll just outline it briefly. So the principal stresses, the hoop stress and the longitudinal stresses at the outer surface of the cylindrical shell are shown acting on this cubic element below. I've got my hoop stress shown there and my longitudinal stress, which is half of the hoop stress. So there is a third principal stress called the radial stress, but that's always assumed to be zero. So the sort of stress in the radial sense, sort of shown here, is negligible compared to what we're considering. So just two stresses we're considering here. Now what you can do, you can draw what's called a more stress circle, and I've actually sketched one over here. And that allows you to calculate the maximum shear stress in a particular plane of the cube that's on the previous slide. So I can't really go to this any detail here because we don't really understand more stress circles. But basically, a more stress circle has direct stress on the horizontal axis and it has shear stress on the vertical axis. So this is my direct stress is shown here, and my shear stress is shown on the vertical axis. And you can draw what's called a more circle here. If you know your principal stresses, for example, we know that the hoop stress vessel is PD upon 2T. We know the value of PD upon 2T. We know actually the longitudinal stress is actually here. It's half of that stress, direct stress. It's actually by this position here it would be. And the radial stress we're always considered to be zero. Those would be our three stresses. And what a Moore circle does, it draws the biggest circle it can between the points on the horizontal axis. And the height of the circle, or the radius of the circle, becomes what's called the shear stress. And again, there's sort of theory behind this. That shear stress value shown there would actually be PD upon 4T. It would actually be half of the hoop stress value because it's actually the radius of the circle, and the diameter is PD upon 2T, so the radius has to be PD upon 4T. So what the Moore stress circle tries to show you is that if you're considering maximum shear stress in a cylinder, the maximum shear stress is PD upon 4T. So that's shear stress. We haven't really considered shear before. It's always been the tension as far as the hoop and the longitudinal stresses are concerned. This is actually a failure in shear here. Exercise 2 is just using the shear stress formula from the previous slide. So a compressed air tank has a diameter 300 millimeters. Again, we'll say it's a 10 millimeters, as we looked at before. We're asked to calculate the maximum shear stress induced in the cylinder wall, given the internal pressure of 4.15 newtons per millimeter squared. So very straightforward little calculation. I've got the solution here. You can see it if you want to put it in your notes. So just be careful. They wanted the maximum shear stress, and the maximum shear stress in a cylinder, we're considering a cylinder here, is PD upon 4T. Okay, so the maximum cylinder shear stress is 31.125 newtons per millimeter squared. Let's consider now a spherical vessel. Okay, we're going to consider a hemispherical or spherical vessels. You do see hemispherical vessels at the end of cylinders. You look at tankers sometimes, road tankers. You'll see at the end of them they have hemispherical shapes there, and that's to keep the stress levels down. When you've got high pressures in these tankers, you reduce the stresses in the end of the vessels by having hemispheres. I'll show you why that is now. We're going to consider spherical or hemispherical, that's half a sphere vessels, all right? So pressure vessels, we've got like footballs here really. So because of symmetry, every point on a sphere is the same as far as the stress analysis perspective is concerned. Wherever you slice the vessel through its diameter, you get the same shape, you get the same area, in other words. That area there, I'm just sort of highlighting, that area is the same wherever you slice it, unlike with a cylinder, of course. So it follows that the concept of hoop and longitudinal stresses developed for thin cylinders becomes purely a hoop stress in a spherical vessel. So we don't have a longitudinal stress in a spherical vessel, because anywhere you slice it, what you see is this circumferential area, so that leads to a circumferential stress or a hoop stress. If we actually consider the generated in a hemisphere or in a spherical vessel, it will purely be a hoop stress. That's all we will have. So the derivation for hoop stress in a spherical vessel is actually the same derivation as for longitudinal stress in a cylinder. because if you think of the pressure here, the force due to the pressure would be the pressure multiplied by the internal area. So it would be the pressure times the internal area. So there's my sort of internal area. That would be the area. So multiply that area by the pressure that's applied. We would get the force trying to literally force apart the hemispherical vessel, and it's reacted by the stress that's in the vessel wall, the sigma. So the reaction force is the stress, and it's multiplied by the area shown there in the orange. It's reacted by that area, which is pi multiplied by the mean diameter multiplied by the thickness. That's how we calculate the area of a very thin annular section. And when you look at that, that's a derivation for longitudinal stress in a cylinder. So it's no great shakes then when we look at the final formula for the hoop stress in a sphere this time. The hoop stress is actually PD upon 40. Next equation 10 there. So again, it's not a big deal to us really. The calculations are very straightforward. We just need to be careful when the questions are stated that are we considering a cylinder in which the hoop stress would be PD upon 2t, or are we considering a hemispherical vessel in which the hoop stress would be PD upon 40. In fact, there would be no longitudinal stress in a hemispherical vessel or a spherical vessel by definition. There cannot be a longitudinal stress. It's always a hoop stress. That's just showing you the same section there. So the stress in any direction that we slice our vessel, the stress that's applied, it's got a hoop stress here, in all locations around the periphery there, is PD upon 4t. So it's half the circumferential stress of a cylinder. So now you might see why people use spherical vessels, why that gas tank, for example, was spherical, because it reduces the stresses as opposed to a longitudinal vessel. And obviously with that gas tank, we're very careful we don't get explosions. So we reduce the stresses by having a spherical vessel, and why you'll find the ends of cylinders are sometimes this dome shape, hemispherical shape, because it's reducing the stress, and so it's less likely we'll have failure. As always, though, of course, we've got to be careful with manufacturing issues. If you're going to have a spherical vessel or hemispherical vessel, there are manufacturing concerns to consider with spheres and hemispheres. So they do only tend to be used when the vessels are subject to quite high internal pressures. It's more for safety issues. When safety issues outweighs any cost issues, we go to these spherical or hemispherical type considerations. All right, so something to be aware of there. And again, this is relates to the failure of a spherical pressure vessel. This is considered failure in shear. And if we go through the same process we looked at previously when we're considering cylinders, using again a more stress circle, this time we find that the hoop stress is PD upon 40, so the maximum direct stress is PD upon 40. So if you draw then a circle between the maximum stress and the minimum stress of course is the radial stress, because that's 0 in this case. If you draw a circle between those two, the diameter of the circle is PD upon 40, so that means that the radius of the circle and the shear stress is actually PD upon 8t. That's the halfway stress, if you like, on the horizontal axis, PD upon 8t. So that's the radius of the more stress circle. So the absolute maximum shear stress in a sphere or hemisphere is PD upon 8t. Okay, and the formula for us. Question 1a, we've got a pressure vessel of diameter 2 meters. In this case, length is 6 meters, made from aluminium alloy. The pressure vessel is constructed to withstand the maximum internal pressure, and the pressure given is 10 times 10 to 6 pascals, and its ultimate tensile strength is 165 megapascals. So slightly different question here in that they want us to calculate the cylinder wall thickness. Straight away we've got the diameter, so little d or big D, whichever you want to use, 2 meters. The length, and I'm not so sure we need the length here, but anyway, they give us the length, I'll take it down. The length is 6 meters, made from aluminium alloy. The ultimate tensile strength, so that's the stress that they've given us, and that'll actually be the hoop stress in our case, because that's the maximum stress in our vessel. So the ultimate tensile strength, or the hoop stress, is going to be 165 megapascals, so that's times 10 to the 6, and that's newtons per meter squared. A pascal is a newton per meter squared, and of course we're given the pressure in the question. I can see the pressure is 10 times 10 to the 6. That's newtons per meter squared as well. So it's information from the question. We've got to calculate the wall thickness. So it's the T that's the unknown in this particular question. So when we design a vessel, a cylindrical vessel here, we know the maximum stress is PD upon 2T. To find thickness, in our case T I've used, so from the hoop stress is equal to PD upon 2T. We're just going to transpose that for the thickness, so the thickness will equal to PD upon twice the hoop stress. Putting our values into the equation, I've got 10 to the 6 multiplied by D, which is 2, and it's all divided by, there's a bit of cancelling here, 2 multiplied by 165 times 10 to the 6. So I can see lots of cancelling here. This means we'll cancel these values off. So 10 to the 6 is cancelled straight away anyway, don't need them. And even the 2's in this case will cancel out. So equals whatever that works out to give us. My value here is 0.061. And that would be meters in my case. So 61 millimeters is what they're saying. That's what I've got, 61 millimeters. Okay, so obviously in some of the questions, you will need to transpose the equation. Transposition is hopefully very straightforward, really. Here's my solution. I've also, you'll see in my calculations, you don't need to do this, but I've just put the D upon T ratio. I'm just sort of checking the ratio, because in the real world, you would obviously have to make sure that the D upon T ratio does comply with the assumptions made that the D upon T ratio is greater than 20, since in this case the 2 meter diameter divided by the 0.061 thickness gives a D upon T ratio of 32.8, so it's greater than 20. So my thin cylinder theory applies. So my calculations are valid here in this particular case. So question 2, a steel pressure vessel of mean diameter 2 meters. We're not bothered whether they give us mean diameter or internal diameter, to be honest. We're just going to use that as D. And a wall thickness of 25 millimeters contains fluid under a pressure, and the pressure this time is 4 newtons per millimeter squared. Assuming the dimensions allow for thin cylinder theory, so we can make that assumption, thin cylinder theory is applicable here, we've got to find the principal stresses within the shell wall. Now when they say the principal stresses, they mean to find the stress, the longitudinal stress, and in the question they've actually got the radial stress as well, because the radial stress is a principal stress. So that's what they're showing here. So this is the hoop stress in the answers. This is the longitudinal stress. You can see it's half the hoop stress. This is actually the radial stress, which we don't normally bother with. We're not usually interested, but I think the question is just trying to highlight to us how negligible the radial stress is compared to the hoop and the longitudinal, because the hoop's 160, the longitudinal is half of that, 80, and the radial stress is equal and opposite to the applied pressure. So the pressure is 4 newtons per millimeter squared, so the radial stress is negative 4 newtons per millimeter squared, or 4 meganewtons per meter squared. So it's very small compared to the longitudinal and the hoop stresses here. So that's why we kind of ignore it. But they've put it in the question anyway, so just to make you aware of it. Okay, so it's just a question of applying PD upon 2T for the hoop stress, PD upon 4T for longitudinal stress, and just stating that the radial stress is equal and opposite to the applied pressure. Question 2A, solution. Extracting the information from the question, the diameter is 2 meters. The wall thickness is stated as 25 millimeters. Notice I've converted that to meters here, so 0.025 meters. The pressure inside the vessel is 4 newtons per millimeter squared. I've converted the pressure into newtons per meter squared, so that's 4 times 10 to the 6 newtons per meter squared. Just for reference, I checked the D upon T ratio, worked out to be 80, so very much greater than 20, so our thin cylinder theory applies here. Then I've calculated my hoop stress, so sigma H in this case is 160 meganewtons per meter squared. We're working in millimeters, that's 160 newtons per millimeter squared. Part 2, calculated the longitudinal stress, sigma L, that's PD upon 40, or half of the hoop stress. So that will be 80 meganewtons per meter squared. And finally, I've calculated the radial stress, sigma R. That's equal and opposite to the applied pressure. The applied pressure is 4 meganewtons per meter squared, shown here. So the radial stress is equal and opposite to the pressure, so that's -4 meganewtons per meter squared. You're still out there? Am I talking to myself? Okay. Yeah, dear. Joys of online, eh? Exercise 3. Okay, so question 3A. So a spherical pressure vessel this time, you need to be careful of that, has an inside diameter of 458 millimeters and a wall thickness of 6.35 millimeters. It's constructed by welding 2 aluminium alloy hemispheres together. So from tests, it's been determined that the ultimate and the 0.2% proof strengths in tension at the weld is 165 meganewtons per meter squared and 110 meganewtons per meter squared. So basically they've given us the ultimate tensile strength and the yield strength of the weld. That's what I'm trying to say. If the vessel is to be designed to have a factor of safety of 2.1 with respect to the ultimate tensile strength and a factor of 1.5 with the yield strength, we've got to calculate the maximum allowable internal pressure for the vessel. And you get this in the codes of practice. This is not an unreasonable exercise. There used to be a British standard. This has gone back years ago. A 5500, I think it was called. It's back in probably the 80s now. There's obviously a more current standard. And it was like all to do with design of pressure vessels. And it had in it, I seem to remember, you had to check your pressure vessel against yielding, which of course can be considered failure, and against ultimate failure. It's sort of broken. And they had these two checks in the actual standard. So realistic information they've given us here. So taking information in the question, we've got the diameter. It says inside diameter, but 458 millimeters. And we've got a wall thickness, that's my T, and that's 6.35 millimeters. We've got the strength, that's a 0.2% proof strength, and they've also given us the ultimate tensile strength. That's on our stress strain diagram. So we know factor of safety is the maximum allowable stress divided by the working stress. So what we've got to do is find the working stress. So from the FOS, factor of safety, is equal to the maximum allowable stress divided by the working stress. We're going to have to transpose that to find the working stress or the permissible stress. That's just normally sigma usually. That's going to be the maximum allowable stress divided by the FOS factor. This is the ultimate first emp. So for the UTS condition, working up to the maximum, our working stress would equal to the maximum allowable stress, which would be the 165, divided by the factor of safety there they've given us is 2.1. Okay, that's one stress. That's based on the ultimate condition, but we've also got the limit condition yielding. So what does that mean? It means to say the yielding is critical. We cannot exceed the 73.2 for the factor of safeties that we're allowed to use. So yielding is the critical one. So basically what we're saying now is that hoop stress is going to be, okay, so now you can just apply your formula. So we've got to find, in this case, the pressure, haven't we? So just transpose it for P. My value I get is 4 times 10 to the 6 pascals. It's the same as 40 bar. Full solution. Type of solution there anyway. Here's question 4A for you to consider. Answers are shown in the brackets, and the full solution is shown on the following slide. Question 4 solution there. It's okay. Here's a few further questions for you to consider at your own pace. Question 5A. Answers shown in the brackets here. Question 5A solution. Question 6A. answers to question 6a in the brackets. Question 6a solution. Note my value here of 7e to the 9 pascals is shorthand notation for 7 times 10 to the power of 9 pascals. Question 7a, answer shown again in the brackets. Question 7a solution. Question 8a, answer shown in the brackets. Question 8a solution. And I will leave you with question 9a, answer shown here, to solve on your own. Question 10a to solve on your own. Slightly different configuration, but I'll let you think through the problem. The answers are shown in the brackets. Here's the bibliography used to help generate this presentation. I hope this has been of interest to you, and thank you for viewing.